Hey everybody, welcome back to the channel. So, look, if you've been waiting around for Google to finally drop Gemini 3.5 Pro, well, actually, keep waiting because they just pulled a massive bait and switch on us. Instead of the flagship Pro model we were all promised back at Google I/O, Google just surprise dropped an entirely new lineup on July 21st. We are looking at Gemini 3.6 Flash, a smaller Gemini 3.5 Flash-Lite, and get this, a literal cybersecurity weapon AI called Gemini 3.5 Flash Cyber that they are keeping on a very tight leash. I've been digging through the benchmarks, the leaked model IDs, the developer guides, and most importantly, how Gemini 1.5 Flash is so blazingly fast because it's been the talk of the town since its release. There is a lot to unpack here. We're going to talk about all of that, plus a really fascinating debate about whether AI safety guardrails are actually making models worse at finding software bugs. Alright, let's just jump right into the big one. Gemini 3.6 Flash. Google is positioning this as their new workhorse model for coding, knowledge work, and multimodal tasks. Now, usually when we hear Flash, we think of the ultra-cheap, ultra-fast tier, right? For example, the baseline Gemini 3 Flash costs something crazy like 5 cents per million input tokens. But Gemini 3.6 Flash is actually stepping into a slightly higher mid-tier space. It costs 150 per million input tokens and 750 per million output tokens. So it's actually cheaper than the outgoing Gemini 3.5 Flash's $9 output price, but it still represents a significant investment if you're running it at scale. But for that price, the speed is genuinely absurd. According to the Artificial Analysis Intelligence Index, Gemini 3.6 Flash is pushing out 275 output tokens per second. I mean, over 200 tokens a second is basically instant when you're looking at a chat interface. And it's not just fast, it's actually incredibly capable. When you look at the benchmarks Google published, 3.6 Flash completely wipes the floor with its own predecessor, 3.5 Flash, and even beats the older Gemini 3.1 Pro on basically every single metric. But let's be real, beating your older models is table stakes. How does it stack up against the rest of the industry? This is where multiple viewpoints really start to clash, because the benchmark results are completely split depending on what you're testing. If you look at OS World Verified, which is a major benchmark for agentic computer use, Gemini 3.6 Flash takes the absolute top spot at 83.0%. It beats GPT 5.6 Luna, it beats Grok 4.5, and it beats Claude Sonnet 5. It also completely dominates on long context retrieval. On the GDM MRCR v2 benchmark at 1 million tokens, it scores 54.0%, whereas GPT 5.6, Luna, and Grok 4.5 didn't even report a score at that length. And the older Gemini models barely scraped 26%. And in case you are wondering why they are comparing it with these models instead of Claude, Mythos, or GPT 5.6 Soul. Well, these models are flagship models, and like I said at the beginning, 3.6 Flash isn't their flagship model. So they are comparing similar price range types of models. And this is a big but, here 3.6 Flash doesn't sweep the board either. If you look at Deep SWE v1.1, which measures long horizon software engineering, GPT 5.6 Luna crushes it with a 67% score compared to 3.6 Flash's 49%. Grok 4.5 takes the crown on the SWE bench pro coding tasks. And Claude Sonnet 5 is the undisputed winner on the MLE bench for machine learning engineering and the GDP Val A V2 benchmark for economically valuable knowledge work. So why are different developers and users forming totally different opinions on which model is actually the best right now? Well, one thing clearly emerging right now is that the spread between these mid-tier models is so incredibly narrow now that raw scores almost don't matter anymore. It comes down to your specific workload and your cost architecture. If you need an AI agent to literally take over a computer terminal and execute long workflows, Gemini 3.6, Flash's OS World Score, makes it the obvious choice. If you're doing pure machine learning research, you're probably going to pay the premium for Claude Sonnet 5. Speaking of developers, there's actually a really spicy rumor going around the community about how this model was even built. Before the official announcement, community users were poking around inside Google Antigravity, which is Google's agentic coding IDE, and they spotted a leaked model IDE called Gemini 3.6 Flash Tiered. User Lentils80 posted screenshots of it, and it immediately sparked a massive debate on X. Why the tiered suffix? Google has never used that naming convention publicly before. Some people think it designates a pricing tier variant, but others suspect it's actually a dynamic routing layer that switches the depth of the AI's reasoning depending on the complexity of the request. And honestly, early hands-on impressions are pretty interesting. Especially, I like this one. This is the Model Showdown GitHub repo from AI Hub Mix, third-party API provider. The setup is straightforward. Same prompt, one shot, real generated HTML artifacts, and no manual cleanup. The four models in this round were Kimi K3, GPT 5.6 Sol, Claude Fable 5, Gemini 3.6 Flash. Gemini 3.6 finished the task. It only cost 12 cents, but the biggest takeaway was that this damn thing finished within 75 seconds. I spent a few hours testing this on my ASR fine-tuning project, specifically looking at the Perkit model. Those models are tricky to fine-tune because the NVIDIA architecture is relatively new and documentation is sparse. Even so, Gemini 3.6 Flash generated functional code pretty quickly. It wasn't a perfect one-shot working code. It took 3 or 4 iterations to get it running smoothly. But the serious speed of Gemini 3.6 Flash made me realize the importance of it. Whenever I ran into an error, I just pasted it back in, and within seconds, the model updated the code for me. It might sound like a lot of back and forth, but the whole process took less than 5 minutes. Since its release, most of the buzz on social media about the 3.6 Flash is all about its speed without losing accuracy, which is far more difficult. Either you get the speed at the cost of accuracy, or you get better results at the cost of latency. So, how does it manage to be so blazingly fast without sacrificing accuracy? I got curious and did a bit of digging, so here's my theory. First off, they achieved much better token efficiency. Google repeatedly emphasizes this. That means the model reaches the same answer using fewer internal steps and fewer generated tokens. It also tends to complete multi-step workflows in fewer turns. Remember that HTML artifact example. Another huge clue about how they did this is that the model is probably more deterministic. Google actually removed user-adjustable parameters like temperature, top K, and top P for 3.6 Flash. Removing these knobs can simplify decoding, making inference more predictable and much easier to optimize. Plus, there's the concept of a better thinking budget. Recent research on Gemini Flash models found that most reasoning gains occur within the first few hundred thinking tokens, with diminishing returns afterward. If Google trained 3.6 Flash to dynamically allocate compute and stop thinking, once additional computation isn't helping, the quality stays the same, but the latency drops dramatically. Rather than spending the same amount of compute on every prompt, the model likely allocates compute adaptively. For anyone who's worked on ASR models, you'll recognize the pattern. It's similar to what happens when NVIDIA's TensorRT makes an existing model much faster without changing its accuracy. The math is largely the same, but the execution becomes far more efficient. So my view is that Gemini 3.6 Flash is primarily an inference engineering achievement. But what about the architecture itself? What's going on under the hood? Some people are speculating it might be a diffusion model. Well, this is a very natural conclusion because diffusion models generate many pieces of an output in parallel and iteratively refine them, which could dramatically reduce sequential decoding bottlenecks. But if it were a pure diffusion language model, we'd expect to see a major research paper, totally different latency characteristics, and API behavior that differs from standard autoregressive models. Instead, it streams tokens the familiar way. The much more likely explanation is a combination of smarter training objectives, aggressive speculative decoding, adaptive reasoning, and highly optimized serving infrastructure. Speculative decoding is huge here. It works by proposing tokens and verifying them, and if the system accepts 90 to 95% of proposed tokens, it feels almost as fast as a non-autoregressive system to the user. Remember how Google implemented small drafter models for speculative decoding in Gemma 4? There is also high confidence that they are using multi-token prediction during training. Again, similar to what they did with Gemma 4. Even if Gemini 3.6 Flash doesn't expose multi-token outputs directly, training with this objective produces better internal representations and makes speculative decoding much more effective. And if Gemini is still a mixture of experts model, which many believe, Google likely improved expert selection, load balancing, communication between GPUs, and token routing efficiency. And what about hardware? Is this just running on their new TPU version 6, Trillium? The short answer is very likely yes. When Google announced Trillium, they said it provides up to 3x higher inference throughput, significantly more HBM memory, and much higher interchip bandwidth. Long context inference is often memory bandwidth limited, so faster memory and interconnects are crucial. Plus, Google already stated Gemini 2.0 was trained on Trillium TPUs, so it would be surprising if they used older hardware for 3.6 Flash. But hardware alone doesn't explain the speed. If Google deployed 3.5 Flash and 3.6 Flash only a few months apart, they're almost certainly running on the same production TPU fleet. They specifically mentioned that 3.6 Flash uses 17% fewer output tokens, takes fewer reasoning steps, makes fewer tool calls, and is more token efficient. Those are model and inference improvements, not hardware improvements. Another reason why I spent so much time digging into improved inference speed is this next model they introduced. Gemini 3.5 Flash-Lite. Its whole philosophy revolves around optimal inference speed. This thing is purpose-built for high throughput, high volume tasks. We're talking 30 cents per million input tokens and 250 per million output tokens. For comparison, Claude Haiku 4.5 costs $1 for input and $5 for output, which is more than triple the price. And yet, 3.5 Flash-Lite is actually trading blows with Haiku 4.5 and GPT 5.4 Mini. GPT 5.4 Mini wins on pure coding tasks like SWE Bench Pro, but Flash-Lite beats it on the OS World Verified Computer Use benchmark and absolutely destroys the competition on long context retrieval. For businesses doing bulk content moderation, translation, or processing thousands of receipts a day, this is a massive deal. In fact, Ramp, a financial company, noted that Flash-Lite hit the Pareto frontier for them on receipt extraction, giving them the perfect balance of accuracy, latency, and cost. But okay, guys, we need to talk about the wildest part of announcement. The third model, Gemini 3.5 Flash Cyber. This is a highly specialized, security-tuned model that Google has locked down. You cannot get open access to this through the standard API. Google is restricting it exclusively to governments and trusted partners via a limited access pilot program. They are running this model inside a new AI agent called Code Mender, which scans code repositories, finds vulnerabilities, actually builds a working exploit to prove the bug is real, and then writes a patch for the developer to approve. And here is where the industry drama comes in. In tests run by Google's Big Sleep team on massive code bases like Chrome, Safari, and the V8 JavaScript engine, Gemini 3.6 Flash Cyber completely outperformed Anthropic's Claude Opus 4.6. In the V8 engine specifically, the Google model found 55 unique confirmed issues, while Claude Opus 4.6 only found 36. But the explanation for why it won is fascinating, and it highlights a major philosophical disagreement in the AI space right now. Google deliberately benchmarked against Claude Opus 4.6, which is an older model, because they claim that Anthropic's newer models actually perform worse at finding vulnerabilities due to their strict safety guardrails. Think about that for a second. The argument here is that if you make an AI too safe and restrict its ability to understand malicious code or generate exploits, you also cripple its ability to act as a defensive cybersecurity tool. You literally cannot have a world-class bug hunter if the AI refuses to look at or generate a cyber exploit. This is why Google is keeping CodeMender on a leash. They openly admit to the dual-use nature of vulnerability research. If this model can build a working exploit to prove a memory corruption bug within 2 hours, which it did in a live Google production service, then a bad actor could use that exact same capability to attack critical infrastructure. So, the debate rages on. Do we neuter the models so nobody can do harm, or do we build powerful offensive models and strictly control who gets the API keys? Let me know where you stand on that in the comments, because it is a massive ethical minefield. The attack on Hugging Face by an autonomous agent a few days back is the best example of this. The platform security team initially tried to use commercial Western frontier models via cloud APIs to evaluate the security incident. However, those models blocked the forensic requests. Their strict safety guardrails could not distinguish a legitimate incident responder analyzing exploit payloads from an actual attacker. So they had to use an open source Chinese model, GLM 5.2. By quickly separating genuine damage from decoy activity, GLM 5.2 allowed engineers to isolate the breach and patch the vulnerability in about an hour. A forensic process that normally would take human analysts several days to finish. I am going a little off topic now, but there is a recent twist in the story. Following the forensic investigation, OpenAI disclosed that the rogue autonomous agent was actually powered by its own advanced models, which had accidentally escaped an isolated test environment during a security benchmark. Anyway, speaking of twists, here is something opposite to it. Yes, a tweet from Logan Kilpatrick again. He basically announced that Google has started pre-training for Gemini 4, calling it their most ambitious pre-training run yet. No mention of Gemini 3.5 Pro. Let us cook, right, Logan? Instead of you guys cooking the model. By the way, when the flagship model is in pre-training, it usually takes around 8 to 9 months for it to get production ready, provided everything goes smoothly. And given the track record of Google and the Gemini model, I think we will get GTA 6 before Gemini 3.5. So that's it for today. Thanks for watching. See you in the next one.